Hi, this is us, the ChainTrace crew. My name is Carter, the man holding the camera, and directly behind me, well, that's Kursat with the impressive hair, our FPGA whiz, and say hello to Anna and Leo, the dynamic duo of coding. Together, we're on a mission to revolutionize blockchain security. From an ambitious vision to long-lasting experiences, ChainTrace began with the goal to safeguard against crypto scams. Inspired by our personal story, our aim is to develop a real-time transaction analysis tool using an FPGA. What's an FPGA, you might ask? It stands for Field Programmable Gate Array. It's a versatile device designed to be configured by the customer or designer after manufacturing. Think of it like a canvas for digital logic artists. In cryptocurrency, it's a digital or virtual money taking the form of tokens or coins. Blockchain is the technology that powers these currencies, a decentralized digital ledger recording transactions. So that's how the name came about. It's our mission encapsulated, tracing the intricate chains of blockchain transactions. This idea began from a personal loss. Our MVP for EC311 final project is one of ChainTrace's key features, our confidence score algorithm. This innovative system analyzes each transaction considering factors like direction, timestamp, method, and value.
Hi, this is Leo.
Hi, this is Anna.
And today we're going to be talking about a transaction tracing algorithm to calculate the confidence score. We take in an input clock and we take in a 31-bit timestamp, which tells us when the transaction is being initiated. Taking input in if the transaction is going into the wallet, and then input method field, which is 2 bits, which tell us if it's a transfer to count the transfers, and then input value, which is 20 bits, and then input new wallet to tell us when it's a new wallet. And then output register 7-bit confidence score to calculate the confidence score, and then output register 7 bits for the 4 factors we use to calculate the confidence score. And then this is the counter for the transfers, and this is a method indicator to tell us if the transfer is being transferred into Tether or Monero. And then we have a 7-bit moving in, which is a counter to count how many transactions moving into the wallet. And then we have a 64-bit moving average value, which calculate the sum of all the total of transactions. And then we have a registered 10-bit start time and end time. And then this is the amount of transactions in that wallet. And then these are just the parameters we set for Tether, Monero, or other method. We have an initial begin, and we set everything to 0. And then we have a case statement. It's a case on method field, and it's always at the positive edge clock. And if we see that it's Tether, we set the method indicator to high. If we see it's Monero, we set the method indicator to high. And then we see if it's other method when we count 1 up for the moving method.
And similarly, for the number of transactions coming in, we just do a case on in, and if the bit's high, then we increment the moving in counter up 1. We set value degrees for the thresholds that we set to deem how high, for the average value, like how high it would be to be suspicious. And this is just the code that has a running sum of the value. Similarly, we always update the end time to be the last transaction in the wallet. So by the time it reaches the end, the last timestamp will be the end time. And we also just increment the counter for the total number of transactions here. And then all of this code is pretty similar. It's to calculate the individual components of our confidence score. So we just have case statement. I mean, we have an if statements for most of this code that just compares the value that we're looking at for the thresholds, and we assign the number accordingly. And then at the end, the confidence score always gets updated whenever any of these numbers change. But we also have to reinitialize these values back to 0 when a new wallet comes in. So we do that on the pause edge clock, but only when new wallet equals 1. And then when you look at the waveform here, we can reload it. It should be the same. Actually, I'll keep it. But this is our test bench we made for it. The first transaction, you can see that all of the in are high, which would be very suspicious, and we set the values to high as well. So basically, we made the first wallet very suspicious, and you can see that the confidence score it outputs is 100 for that. And then for the next value, we altered the in and out ratio so it's more even. We also lowered the value amount and made the timestamps more spread out. You can see by the end of this transaction, by the time the wallet's done being analyzed, the confidence score was much lower than the original.
ChainTrace flows from Python to FPGA, a symphony of code and hardware. Our workflow is rather simple. My Python code makes an API request to Etherscan. Once we receive the data in JSON, I reduce it further into binary per the confidence score requirements. I then initiate a serial communication with the FPGA on COM4 with 9600 baud rate and send the data over to the FPGA. The FPGA, initially coded by Kursat, will receive this data and perform some calculations. I added a layer of logic to Kursat's robust transmitter and receiver modules.
Let's take a look at the source code of our project. On the left side of the screen, under Design Sources, you can see that the top module of our project is UART Test. This is the main module that makes everything work by completing the UART connection between the PC and the FPGA. The UART Test module has two modules instantiated within it. These two modules are UART Top and Button Debouncer. From these two modules, UART Top is the one that handles the actual UART connection, utilizing FIFOs, a receiving module, and a transmitter module. Now let's take a deeper dive into UART Top. In here you can see that the UART Top has been instantiated to be a certain number of data bits, a certain number of stop bits, meaning using how we implemented oversampling, and this is the baud rate generator counter limit that is a result of the 9600 baud rate that we established in our project. These inputs are used to connect everything from all of the other modules that we have created in the project. The baud rate generator is instantiated here. After the baud rate generator is instantiated and a baud rate is established, we move into the UART receiver and the FIFO. The FIFO takes a single byte at a time from the serialization established between the PC and the FPGA by our Python script. This FIFO, after taking in the data, transmits the data into the larger FIFO, which takes in the data and stores it byte by byte until it reaches its limits, which at the very most at this point in our project can be 651 due to the baud rate. After that, the data is now finally in, stored, and ready to go. Now we send our data to our transaction tracing algorithm, and then after that we finally transmit our data back for further processing.
Remember, FPGA design is more art than science. It's about precision, timing, and touch of genius. From the thrill of getting serial communication up and running to the head-scratching moments with our display, every step taught us something valuable. If you're as excited about solving complex puzzles as we are, give us a shout. We're always looking for fellow adventurers. Thank you for tuning in. A shout out to everyone who's supported us thus far. Here's to more breakthroughs and innovations with ChainTrace.